Welcome back, guys, to Math TV with Professor V. This is video lecture for linear algebra, part 2 of section 2.3 on the inverse of a matrix. So picking up where we left off last time, now we're going to look at Theorem 2.8 properties of inverse matrices. And it states the following: if A is an invertible matrix, K is a positive integer, and C is a non-zero scalar, then A inverse, A raised to the K, C times A, and A transpose are all invertible, and the statements below are true. So statement number 1 says the inverse of A inverse gives you back A. That seems pretty reasonable. If you take A, raise it to the K, remember K is a positive integer, and then take the inverse, that's equal to A inverse raised to the K. So we have this commutative property going on here. If you have C, a scalar, times matrix A, and then you take the inverse, the result is 1 over C times A inverse. So basically this becomes the multiplicative inverse of C. And then A transpose, if you take the inverse of that, you are left with A inverses transpose. Pretty cool. The proof of this is in the textbook, in most textbooks too, and we're going to just look at an example here where we compute A raised to the negative second power 2 different ways and show the results are equal. And we're going to show it for this little 2 by 2 cute matrix here, 2, 7, negative 5, 6. So how are we going to do that? We're actually going to utilize property number 2 right here in order to do that, because we're asked to show it 2 different ways. So one way I'll show using the left-hand side of property 2, and the other way I'll show using the right-hand side of property 2. So what my goal is to show that A squared inverse is equal to A inverse squared. So basically K equals 2. All right? So 2 different ways. Okay, I'll start off with the left-hand side here. First, I'm going to find A squared and then its inverse. So the square of a matrix you find just by multiplying the matrix by itself. We can do that. We're old pros at this now. 2, 7, negative 5, 6. And then same thing over here. 2, 7, negative 5, 6. Alrighty. And let's go ahead and compute that product. So remember, you take the first column here in the second matrix. I like to just write it up top, and then you can do that product. Usually I do it in my head. So this is 4 minus 35. I'll write that out here just because we're probably warming up. Use a column to make a column, and then you take the next product. So negative 5 times 2, 6 times negative 5. That's going to be negative 10 minus 30. And then we repeat with the next column. So we'll take now 7, 6, write it up top here. This product 14 plus 42, that will go over here, top left entry. And then 7 times negative 5, 6 times 6, that's negative 35 plus 36. All right. So what are we left with here? This is going to be negative 31, 56, negative 40, and 1. So this is A squared. I'm not done though. I need to now find the inverse of this matrix. So we've studied how to do this. We're going to write out A squared. And then on the other side, put the identity matrix, size 2 by 2, transform A squared until it's the identity matrix. And then on the right, I'll have the inverse. So let's see what we've got going on right now. We've got negative 31, 56, negative 40, and 1. And then on the other side, remember, we put 1, 0, 0, 1. And then time 2, transform. So this needs to become the identity matrix. So starting off, I'm going to make this top left entry a 1. Ooh, How ugly. Okay, so I'm going to take a negative 1 over 31 times row 1, and that's my new row 1. And you might say, oh no, I don't like these fractions. Oh well, get over it. You're an advanced math student. You can handle it. So this will be 1, negative 56 over 31, negative 1 over 31, and 0. Okay, see, that wasn't so bad. Negative 40, 1, 0, 1. Very nice. Okay, next we turn our attention to row 2, column 1. That needs to be a 0. We do it using the pivot, or that 1 that we just created. So I'll take 40 times row 1, add it to row 2, and that's my new row 2. Very good. So let's see what we have. This will be 1. This isn't changing. Remember, row 1 stays the same. Let's rewrite it first so we don't get carried away. Negative 1 over 31, 0. Okay, this is going to be a 0. If I take 40 times row 1, just multiply that by the numerator. So you're going to have negative 2,209 over 31. And positive 40 times negative 1 over 31, that's going to be negative 40 over 31 here, and 1. Okay. See, things are turning out nicely. Okay, now we turn our attention here. Row 2, column 2, that needs to be a 1. So I'm going to multiply all of row 2 by the reciprocal. And yeah, opposite reciprocal. So negative 31. No, just the reciprocal, excuse me. Over 2209, row 2 is the new row 2. And let's see what we are left with. We will have 1. Okay, row 1's not changing. Let's rewrite it now. Negative 56 over 31. 1 over 31. Oops, negative. And 0. And then now my new row 2 will be 0, 1, 40 over 2,209, and negative 31 over 2,209. Love it. Okay, almost done. Last thing is we need to make this entry a 0 using the pivot that we just created. So let's see, what would we do? Well, I would take 56 over 31 times row 2, add it to row 1, and that will be my new row 1. And then we should be done. Okay. So let's see, now we have 1, 0. 1 over 2,209 and negative 56 over 2,209. 0, 1, 40 over 2,209, and negative 31 over 2,209. Beautiful. So now what have I done? I found the inverse because I have the identity matrix on the left, and on the right now I have the inverse of a squared. Okay, so we found it one way. We have found that the inverse of a squared is, I can factor out that 1 over 2,209, and then it looks better. 1, negative 56, 40, and negative 31. Okay, there is another way to find the inverse of a 2 by 2 matrix, but we will go over that later because we need to learn about determinants first, and we haven't learned about them yet. Okay. Now we need to find the same quantity using the left-hand side of the identity. So what we're going to do is find the inverse of a and then square it. Okay, so we already did this portion here, a squared and then the inverse. Now we need to go the other way. So continuing, I need another sheet of paper. Okay, love it. Now, method 2. We're going to find a inverse first and then square it. So just to remind you, matrix A is 2, 7, negative 5, 6. Okay, let's find its inverse. So we've got here, same process that we just did, A, then we're going to write the identity matrix on the right. So we have here 2, 7, negative 5, 6, 1, 0, 0, 1. Okay, this is going to be nice, right? Because we don't have such bizarre numbers. All right, so what we need to do is create a 1 up here, create our pivot. I could divide by 2. Sometimes I don't. I do some spicy stuff. One thing we could do, if I make it a 6 and add row 2 to it, then I'd have a 1 and then I'd keep things fraction free up until probably the end. So let me show you another thing you can do. Just once in a while, keep things interesting. We can take 3 times row 1, add row 2 to it, and that'll be our new row 1. All right, and then look what's going to happen. I'm going to have a 1. This is totally legit. These are legal row operations. The math police will not be coming for me. So 3 times row 1, that's going to be 6 plus negative 5, 1. 3 times 27, 21 plus 6, 27. Oh, look at this. See? And no fractions just yet. Sometimes it makes life rough when you bring them into the picture so soon. Okay, very good. Let's scoot this over. Now that we have a pivot in that entry up there, why don't we go ahead and make this entry down here a 0. So how are we going to do that? Using the pivot, I'm going to take negative 5 times row 1 plus row 2. That will be my new row 2. Okay, so see what's going on here. Row 1's not changing. Let's rewrite it. 1, 27, 3, 1. And then we'll have 0, 141, 15, and 6. Good, good, good. All right, next we turn our attention to this little entry. That needs to be a 1. I'm not going to get fancy with the 27, so let's just do 1 over 141 times row 2 is the new row 2. We have to introduce the fractions now. There's no way around it. So this is going to give us 1, 27, 3, 1. That stays the same. Then 0, 1, 5 over 147. Hold on, bear with. Yes, and 2 over, it should just be 47, excuse me. 5 over 47 and 2 over 47. Okay. Good, good, good. Everything's looking lovely. Next, we need to make this 27 a 0. So, using that pivot, I'll take negative 27 row 2 plus row 1. That's my new row 1. And then we'll be done. Isn't that exciting? We'll be done finding the inverse. So we'll have 1, 0. This is going to be 6 over 47, negative 7 over 47, 0, 1, 5 over 47, 2 over 47. Lovely, lovely, lovely. So what do we have now? Well, we have the identity matrix, order 2 on the left, and then A inverse on the right. So what I want to point out is that A inverse is equal to, I can factor out that 47, 1 over 47, and then write the rest of the entries as 6, negative 7, 5, and 2. Okay, very good. Very good. So now all that's left is we have to square this inverse. And I want you to notice, you can write it out. Let's write it out twice. So it's 1 over 47 times 6, negative 7, 5, 2. And you it will be a big game changer to factor out that 1 over 47, because you'll notice now the multiplication of the matrices is so much easier, right? Because we're not going to have all these fractions going on. So when you multiply two matrices, but you also have scalars like that involved, you can just multiply these by each other. So we can rewrite this as 1 over 47 squared, and then go ahead and multiply the matrices. So 6, negative 7, 5, 2 times itself. 6, negative 7, 5, 2. Okay, see how nice? And then we have 1 over 47 squared times, I'm just going to do this in my head. Hopefully you guys are at the point where you can just imagine, right? There's a 6 and a 5. So it's going to be 36 minus 35, 30 plus 10. Then do the same thing with the next column, negative 7, 2. Do it in your head. So that's going to be negative 42 minus 14, negative 35 plus 4. And then we're left with 1 over 2,209 times 1, negative 56, 40, and negative 31, which is the same that we got earlier. Had you forgotten what we got earlier? I know. It feels like eons ago. Let me scroll up so you believe me. Perhaps you wrote it down though. Okay. I was concentrating, so sorry I wasn't cracking jokes like I normally do. 1, negative 56, 40, negative 30. 31. Yep, that's what we got. Wonderful. Now, just to clarify, we did not prove property 2. I only showed that it worked for this particular case, right? When you do a proof, it has to be general. You can't just go up and say, hey, look, I showed for a specific case it's true, therefore I proved it. No, you didn't. Okay. Good. Now let's look at another theorem. Moving on. 2.9. Ooh, I love this one. The inverse of a product. So if A and B are invertible matrices of order n, then AB, their product, is invertible. Ooh, and AB inverse equals B inverse times A inverse. How fancy. So we're going to prove it. I know, guys, I know. So let's see. What they told me is A and B are invertible matrices of order n. So let A and B be invertible matrices. Another, let's practice using our vocab. That also means that A and B are non-singular. Okay. And if they're invertible matrices, what does that mean? Well, that means that A inverse and B inverse exist. We also know that that means that A times A inverse is equal to A inverse times A, and that'll give us the identity matrix, as well as the fact that B times B inverse is equal to B inverse times B, which gives us the identity matrix. So I've done nothing more here than take that one statement that they told me, that A and B are invertible, and write down everything that that means, which is why it's so important, you guys, that you know your definitions, because this is going to be the building block for writing out this proof. You know, these statements here, this one and this one, these are crucial. So if you don't know, hey, A and B is invertible means that, then yeah, you're going to have a really rough time doing proofs. Okay. So what are we asked to show? Two things, actually. We have to show that AB is invertible, and that second thing, this is what its inverse is equal to, B inverse times A inverse. So let's come up with like a little game plan. So we have to show that AB is invertible. So I need to show that AB inverse exists. And to do that, I need to show that AB times AB inverse is equal to AB inverse times AB, and that would give me the identity matrix of order n. Okay? Well, let's see. How would you go about doing it? They kind of already gave me a hint as to what the inverse is, because they told me I need to show that it's equal to that. So I'm going to start off multiplying AB inverse by B inverse A inverse. So watch what I'm going to do. So step one, I'm going to take matrix AB and multiply by what I'm trying to show its inverse is equal to. Okay, this is fine to do because I know B inverse and A inverse exist, these two quantities here. I'm, deciding to multiply by B inverse A inverse in this way because I'm trying to show that that's the inverse. So let's see what we can do here. Just using some of our matrix multiplication properties. I know it's associative. I'm not going to reorder things. Don't worry, guys. So I'm going to have A times B inverse times A inverse, right? Totally cool. I didn't do anything wild. B times B inverse, since B is invertible, that's A times I, identity matrix, times A inverse, right? Yes, good. B times B inverse equals I. That's all that's going on right there. And then A times I is A times A inverse, and then this gives me back the identity matrix. Okay. So now I took AB, I multiplied by B inverse A inverse on the right, and I got the identity matrix. Let's see if we get the same result when we multiply by B inverse A inverse on the left. You do have to show multiplication in both orders because remember, matrix multiplication is not commutative. So again, I'm going to go ahead, use the associative property, A inverse times A, and then little b's hanging out there. A inverse times A, that's just the identity matrix. B inverse times identity matrix is B inverse times B, and yep, this gives me back the identity matrix. So combining the results from 1 and 2, what do we have? Well, we have that AB times B inverse A inverse is equal to B inverse times A inverse times AB, which is equal to the identity matrix. So what does that tell me? That B inverse A inverse is the inverse of AB, which means that if you want to find the inverse of AB, it's equal to B inverse A inverse as desired. Okay, so I basically knocked out showing both things, that AB is invertible, doing 1 and 2, and I found the inverse when I was showing that it was invertible at the same time. And yeah, obviously it was helpful that I knew to bust out B inverse A inverse because that's what the proof told me to show. So that's how I was inspired to multiply like so. So a lot of the times there's hints within the proof, to kind of guide you, but you just need practice so you can feel comfortable doing them on your own. That's the tricky thing about proofs is there's some techniques, but it's not like you solving exercises where you're like, oh, I've done one, I got it, they're all the same, I'm just going to copy the same process. No, you have to kind of think through logically depending on the scenario. Okay, now let's use this little shortcut method. Find AB inverse for the following matrices. So they gave me matrix A, matrix B, and then they also gave me the inverses of A and B individually. So, before this theorem that we just learned, the old method, what would we have done if I had asked you this earlier? You would sit there, find the product AB, and then you would find AB inverse using your row operations, right? So you would make that big matrix with identity matrix, order 2 on the right, etc., etc. New method's going to be a lot more relaxing, less tedious. So if I want to find AB inverse, it's just the product of B inverse, A inverse, and then I can use the given matrices, the given inverse matrices. Oh, how nice. Fabulous. Okay, so AB inverse is equal to A inverse, or B inverse, excuse me, times A inverse. I'm not too keen on multiplying these two matrices by each other the way they're written right now, because look at that fraction situation going on. So what I'm going to do is rewrite B inverse as 1 over 11 times 5, 2, 3, negative 1. And then A inverse is, oh no, I can also take out a 1/7. Yes, now I'm liking this. Negative 2, 1, 3, 2. And then remember, we did this earlier when we squared one of our matrices. So you can just multiply these constants by each other out front. So we'll have 1 over 77, and then just multiply the matrices. So negative 2, 3, that would be, let's see here, negative 10 plus 6, and negative 6 minus 3. And then up top, let me put column 2, 1, 2. So that's going to give me 5 plus 4 and 3 minus 2. So then we're done, and it was pretty painless. 1 over 77 times, what do we got here? Negative 4, negative 9, 9, 1. Love it. Okay. If you don't believe me, you can sit there and multiply out B inverse and A inverse with all those fractions. Have yourself a little challenge sesh, okay? Good. I got a couple more proofs for you, and then we are done with this lesson. So Theorem 2.10, cancellation properties. So if C is an invertible matrix, then the properties below are true. Property 1. If AC is equal to BC, then A is equal to B. And property 2, if CA equals CB, then matrix A equals matrix B. Okay, so to prove this, let's see what they told me. Not much. They just said C is an invertible matrix. So what do we know? Write down what that means. That means a lot of stuff. So let's C be an invertible matrix. That means that C inverse exists, okay, and that C times C inverse is equal to C inverse times C, which gives me the identity matrix. Okay, so let's start off with property 1. If AC equals BC, so that means we can assume that's true. So let AC equal BC. What do I need to show? I need to show the then statement. So I need to show that A is equal to B. Well, all I have is this C inverse I can play around with, so let's multiply by it. You have to be careful which side you multiply on, because matrix multiplication is not commutative. So in order for C and C inverse to cancel out, I need C inverse to be multiplied on the right. Yes? I know you have to be so careful. Careful, careful. Like this. If you put it on the left side, it would be wrong. Wrong. Okay, now associative property time. A times C, C inverse equals B times C, C inverse. Then I have A times the identity matrix equals B times the identity matrix. And I'm left with A equals B, which is what we wanted to show. What did I just do there? You could sometimes do like a little doot, doot, doot. I'm done. It's satisfying, let me tell you. Okay, property 2, very similar now. Do you think you could figure it out on your own? Let CA equal CB. I need to show that A is equal to B. This time I'm going to multiply by C inverse on which side? On the left. Very good. C inverse times CA equals C inverse times CB. Now associative property time. Don't skip steps. This is the thing. With a proof, it is already true. You're just being asked to show the logical process. So no, you don't get to skip steps and think it's obvious, okay? That's the whole point. You have to show it. I times A equals I times B. So A equals B. Beautiful. Okay. See, we're becoming professionals at proofs. I've got one more theorem and little example, okay? Last theorem of the lesson, Theorem 2.11, systems of equations with unique solutions. So if A is an invertible matrix, then the system of linear equations AX equals B has a unique solution, X equals A inverse times B. If you'll remember, we earlier proved that there's only 3 possible scenarios for systems of equations, linear equations. Either there's a unique solution, no solution, or infinitely many solutions. And now we're being told that if A is invertible, then we have one unique solution. So that must mean no solutions and infinitely many occurs when the matrix is not invertible. Ooh, we'll look at that later. But anyways, let's work on this proof here. So let A be an invertible matrix. Since they told me I could assume that. And what does that mean again? That means that A inverse exists. Also, that means that A times A inverse is equal to A inverse times A, which is the identity matrix. Okay, so I'm going to let AX equals B be a system of linear equations. And what I need to show is that X is equal to A inverse, times B. We've already shown that the inverse of a matrix is unique. We did that proof by contradiction earlier. So if I show that X equals A inverse times B, then I'm done. That is a unique solution since we know that the inverse of A is unique, okay? So what do we have? We have AX equals B. I'm going to multiply again on the left by A inverse. And then we're pretty much following the same process we've been doing earlier. A inverse times A times X equals, A inverse times B. So we have identity matrix times X equals A inverse times B, which gives us the desired result that X is equal to A inverse times B. If you want to write yourself a note, we already showed that A inverse is unique. That's a theorem. So that's established. So this solution is unique also. Okay? Very good. So now we're going to look at an example where we can solve a system of linear equations using an inverse matrix. So here we have a system of 3 equations with 3 unknowns. Let's write out the linear system using matrices. So A is the coefficient matrix. If you'll remember, we did this a little while back. So matrix A is going to have the coefficients of all the variables on the left-hand side of the equation. So it would be 1, 2, 2, 3, 7, 9, -1, -4, -7. This is matrix A. Then the variables are listed as a column vector, x1, x2, x3. So this is matrix or column vector X, okay? And then column vector B are all the constants on the right-hand side of the equation, 2, 8, -5. So here we have AX equals B. To solve the system, column vector X is equal to A inverse times B. Okay, so basically the crux of the problem comes down to finding A inverse. And how do we do that? Well, we would do Gauss-Jordan elimination on the matrix A with identity matrix order 3 on the right until we get identity matrix on the left, and then A inverse would be on the right. Yes? Here we go. Just kidding. You guys, we actually found A inverse in a previous example in this lesson. Well, in part 1. So you'll have to watch part 1 if you haven't already. So we have from earlier, ooh, good thing I was so nice, I give you a system of equations that had the same coefficients as the inverse we found earlier. So A inverse is negative 13, 6, 4, 12, negative 5, negative 3, and negative 5, 2, 1. Okay, so all I need to do is multiply that matrix by column vector B, and we will have our solutions. So x, which is x1, x2, x3, is equal to this A inverse. A inverse is negative 13, 6, 4, 12, negative 5, negative 3, negative 5, 2, 1, times 285. Negative 5, excuse me. Okay, so let's see what we're going to be left with here. Let me write it up top. 2, 8, negative 5. And this is going to give us negative 26 plus 48 minus 20. 24 minus 40 plus 15. Negative 10 plus 16 minus 5. Okay. And then the result is our solution. How exciting. This is going to be 2, negative 1, 1. So the solution here right now is written as a column vector. You could also write it as an ordered triple or a row vector. So if you wanted x1, x2, x3 like this, then you would write it out as 2, negative 1, 1. And then now it's basically a row vector. Okay, so that concludes the lesson on inverse matrices. Our next video coming up is elementary matrices, so stay tuned. Subscribe to the channel if you haven't already. Give this video a thumbs up, and if you'll notice, there's a join button now on my channel. So if you join, it's just $4.99 a month to become a member of this channel. Some of the perks are you get early access to new videos, members only polls, loyalty badges next to your name in the comments and live chat, and member shout outs. So stay tuned. I got lots of exciting stuff coming your way, guys.